Hello everybody and welcome. Again, we are leaving behind our trusty old friend, the Siemens PLC, and we are going to be using a Raspberry Pi to control this VFD over Modbus. Now this will work for any VFD over Modbus, although your register addresses may be different to our trusty old M100 here. Now, just like the last video, we're using a USB to RS485 converter, and the wiring on this guy is crazy simple. So our A terminal is going into our orange and white, our B terminal is going into our brown, and our signal ground is our brown and white. That easy. Okay, so we're actually starting out with a bit of a shout out to an Alexei Kolyupiev. I think it's Kolyupiev. I'm sorry if I'm butchering your name, but he put in the comments on the last video an absolutely awesome suggestion. So if you remember from our previous video, to find the location of the USB, we basically did a text dump of the dev file, the dev directory, put our USB in, did another dump, and then ran a difference, a diff function on that to see what had changed and get our USB location from there. Now, what Alexei has suggested is to use, let's bring across the terminal here, is to use this dmessage solution. And I've tried it and I absolutely love it. So thank you, Alexei. I am stealing this and I'll be using it a lot in the future. So all we need to do, should say the USB isn't plugged in right now. So I'm going to do dmessage. So this is just going to let us see what a certain part of the kernel is up to. We can give it a flag for W, small w for this one, to look at new stuff. And then we're going to AND it with another function. And AND in this is just the pipe symbol. And we're going to AND it with a grep function. Very simply, a grep is kind of like a searchy filter type thing. So we're going to grep it and we're going to look for this keyword TTY. So it might look a bit weird, but all this is saying is any new messages in this part of the kernel and anything that matches this TTY we want to know about. So we press enter on there, it'll give us a bunch of stuff. And now if I go and plug in this USB, boop, and we can see here, this line has just popped up saying, you know, you just inserted something and it is TTY USB 0. So all of that faffing about in the previous video completely solved with this awesome little thing. So thank you very much, Alexei. Need to get you a medal in the post or something. All right, so let's get into how to make this thing actually work. So for Alexei's super trick here, we can just Control C to finish that up. Now we're going to go through the code in a moment. I'm just going to show you this working just innately, just so you know what's actually going on as the code's running. So inside of our file here, we should have a whole bunch of different modules I've put together. Do let me know if you want me to go into kind of more simplistic videos on, you know, how to do it, so you're, you know, referencing different modules and different things and whatnot, because that's something I'd quite like to do. But just let me know if you'd be keen for kind of less niche control system videos. But anyway, the one we want to run is VFD control, and it kind of references all of these other things. So we're going to run it on Python 3. Right, okay. So one thing I have noticed, which is a bit annoying, is the video capture software I'm using doesn't pick up the actual gumph that's coming through once it's running. So we run this program. You can see this okay. This is where it's prompting the user to put in a drive mode. So do we want to run it in forward, reverse, or stop it? So I'm going to run the VFD forward, so FWD, press enter, and it's going to ask us for an input speed in hertz between 0 and 60. So let's pick something nice. Let's pick 46.76. Why not? And we send that. And you can kind of see it's, well, from your point of view, it'll be flickering all over the place. I might do I'll just record the screen old school and put that up there as well. But this is telling us what is going on with the VFD, and it's not only have we commanded the VFD to do something, we're also getting information back from it. So what frequency are you currently at? What's your current, your output voltage, your DC bus voltage, your total power. And then there's this other thing called operation code, which we'll get to later on what that is and how from that we can infer what's actually going on. So you can see in current operation, we're actually being told we're running the motor forward, which does make sense. So if I bring this back to stop now, press Ctrl C, put in a new drive mode, so stop, say 0 Hertz for that, and we can bring this back down to 0 Hertz. And you can see we're decelerating in forward to stop. There we go, nice. So let's have a bit of a look now at deep diving the code as to how we actually achieve this and how we put this out to the user. Okay, so bringing up the code itself, like I said before, the code is actually split into these 4 different scripts. The main script that we actually run is this VFD control, and it references all of these others that we have a whole bunch of other information in, which we'll go through in the course of this video. But let's just go through the skeleton of the thing and see how it works. First thing we do, obviously, we're using minimal Modbus to do all of this stuff. So we import the minimal Modbus library, easy. And then we import all of the modules that we've put together. We import those as well. I'm very lazy, so instead of typing Modbus settings out all the time, I've just imported that as MB. So every time you see anything referencing MB, you know I'm referencing this Modbus settings script here. And anything that is referenced as stat is the statistical display, which is this guy. And also same with the user inputs. But for some reason, unbeknownst to myself, I just imported that as user inputs for readability. And then a few just things to make things just work nicely. So we've got imported time, imported sleep, and OS and sys, just so we can do a few fun little things on the back end. So in this main script, what are we looking at? The first thing we do is we just initialize our flags. As you saw when we actually ran the code, there's 2 things that we need to tell the program. We need to tell it what drive mode we want, like forward, reverse, stop, anything like that. And we want to tell it what speed it is. And these are just 2 flags that let the program know if we have done that correctly. And to move information around, what have we actually told it to do, we have these things. I've initialized them to 0, but the drive package is what we actually send to the VFD. And same with the speed package. So what direction are you going? How fast are you doing that? So nice and easy, just initializing those little packages there. What we also do, you can see an MB here. So we know that we're referencing code in this Modbus settings script. But basically, as I've went through in the previous videos, minimal Modbus, even if you want to have a look at something or write something at an offset of, say, 40,001, you don't put 40,001 as the register address, you put 1 because it kind of covers that when you give it the function code. So a function code of 3 means you're doing something with the holding registers, so it knows that they start at 40,001. So if you input a holding register name from the documentation that was like 40,017 or something, what this does is basically gets that minuses 40,001 from it to give this write start variable the correct value for minimal Modbus, basically making sure that it's not 40,001, it's what minimal Modbus actually wants. So once we've done all that, we just jump into the main loop, and this is where we need to start diving off into these different scripts. But as a very basic overview, I should say as well, all of the code for this is all on my GitHub. I'll put a link in the description, so please feel free to download it, use it, modify it, whatever you'd like to do. So this main loop here, we're just checking these flags to start with, really. So we see, have we set the drive correctly? We start off with that false, so that brings us into this loop. If we haven't do that, it tries to make this drive package, so this space for information, and it basically, whatever the user puts in, drive package then equals, which is obviously, you don't just want to do that, because if the user puts in anything but pristine data, you're going to run into massive issues. So if you haven't put anything in, it gets what the user puts in and makes it equal to drive package. Then we do a few checks on that. So if this drive package, I'll show you the insides of this in a second, but basically if a drive error comes back, something's gone awry somewhere. So if drive package is equal to the string drive error, we just print drive not recognized. We make sure that that flag isn't set as completed, and then the program will just have to loop back to the top and just give the user another chance to input data that's not messed up. So if all that works well, we are able to move down to here, and basically we tell the user what drive mode that equates to, because you saw me putting FWD in to go forward. That is not what's fed to the VFD. What we actually need to feed to the VFD is a bit different. Again, we'll go into that in a moment, but this basically tells the user, okay, that is this integer, and because we know it's all worked properly, we then set drive set to true, so we know that that's done. Next part of the code does pretty much exactly the same thing, but on the speed side. So we can check the two flags. If drive set is true, which it would be if we've just done all this properly, and if speed set is false, like we haven't put a speed in yet, we move on to that next portion of the code. In fact, we can actually do this here. So if I run this program again, so right now we're in this top bit of the code here. Both the flags are false, and we just want to go and do something. So let's put it in reverse. So I put REV in, and we can see here what has happened is there hasn't been an error, and we've got to this portion of the code where it's given us back what it's actually sending to the VFD, which in this case is 4. Now, if you remember from the last videos, aficionados amongst you may know that the integer 4 is effectively setting the third bit high. So it's not the 1's place, it's not the 2's place, it's the 4's place. But we'll dig into that in a little more depth shortly. And now it's asking us for this input speed, because our drive flag is true, but our speed flag is false. So we are here, and it's asking for some input. And again, we do the same thing. We need to put in a number. Well, we can actually put in anything. Again, that's a danger. This needs to be a little more involved because there's a few ways in which it can go wrong. But basically, inside of this, the user inputs module, it's going to be looking at the number, making sure that it is actually a number. So if I put in the letter G, or the Batman symbol or something, it's not going to try and fire that through to the VFD. So we can either get back not a number, and if that's the case, it's going to tell the user that's not a number, but because of how the flags are set, it will just loop back around to allowing you to input that data again. Or if it is a number, but it's outside the limits that we want to send to this VFD, we'll get an OL returned, and then we can just tell the user that was under or over what you're allowed. So let's actually try that. So I've said hertz between 0 and 60. So if I put in 89 hertz, you see here, speed under or over limits, drive mode is still set to 4, and it's asking us again to input the drive speed that we want. So let's try this again and say a nicer number, 34.7. Go on that, and huzzah, it's working. And we can see on the VFD, yeah, it's actually changing to run in reverse at 34.7 hertz. So once we've done all that, we know that something nice happens, and that is this part of the code down here. So this is basically looking if the drive set is true and the speed set is true, i.e. all of the data we have given it is good data. This is the actual Modbus part. So this is just sending to VFD. Now this is in the user input section. We'll get into the actual Modbusiness of it, but this is where it groups all that data together. So you can see the drive package information's here, the speed package information's here, and the right start address is here. It sends that off, and that gets fired out to the VFD. So this is us telling the VFD what to do. Now, once we've done that, we want to give the user some sort of idea what is going on with everything, and that is this part of code here. So we run through this, And if drive is set and speed is set, so again, checking those flags, if they're all okay, and this is why we imported OS, we can clear the screen. And I think this is what's playing merry hell with the screen capture stuff as well. But we clear the screen on that terminal, and then we run the code stat.readVFD. So now we know we're running something in there, and that's a loop in itself. But we'll get to that. We'll get to that after. So let's have a dive into the sub modules themselves. So the first one we actually need to look at is well, I suppose we should actually look at the Modbus settings, because the Modbus settings is not running any code in there, it's just a reference for all of the other stuff. So if you've seen the previous videos, it's pretty much exactly how you would set up these devices in any other circumstance. And I've separated out into three parts. There's the general settings, which don't change depending on if we're reading or writing. So here I've just hard-coded the Modbus address because I'm just addressing this one VFD. I don't need to make it any more clever than that. This USB port here, and thanks to Alexa, we now have a much easier, faster way of working out what this number should be, our baud rate, bit size, etc, etc, etc. These don't change if we're reading or writing, so all of these just stand alone as this is just the spec of the Modbus. So we can reference this when we're doing different things to read or to write. We can just do, well, it'd be MB because I've imported it as MB. Is it MB? I think it's MB. As MB, yes. And just reference these directly to make that instrument for us. And then we have some stuff that is specific to writing. So I know from from our previous work on this VFD that our first place that we want to write is the register address 40,005. Now, like I said, if we put 40,005 into minimal Modbus, that won't work, which is why we need to have this write start bit of maths here. So mb.control offset, and then take away 40,001 from that. So it's going to get this control offset and take 40,001 away from that, and that'll give us the right place. Now, if we pull up the documentation for this VFD, which is also linked up here if you wanted to have a look. So that brings us here. And if you remember from the last VFD video, 40,005 is our command frequency. So this is, are we running, the frequency. So what speed are we running at? And then 40,006 is the command. So are we running forward, reverse, stop? So stop is the first bit. So we would give it a 1 to stop. The second bit, or the 2's column, if you will, is for running forward. So we send it 2 when we want to run forward. And as you saw in the beginning of this video, when we told it to run in reverse, it said, okay, I'm going to be sending a 4 to this VFD because the third bit is the 4's column. So the 4's column, if you will. So when we send it a 4, we know we're going in reverse. So it's that simple, exactly what we've done before. And there we go. On the read settings, we're just looking at different stuff. So this is telling the VFD what to do, and then when we're reading back what on earth is the VFD up to, we're looking at a different place in memory. And this starts at 40,009. And we're wanting to read, well, we're only wanting that to actually read about 5 bits, but I've done 8 just for the lols. But let's have a look at what is actually at 40,009, because this is going to make a lot more sense very, very soon. So if we carry on down here, random blank page, here we go. So this is what we're looking at. So when we interrogate these different registers, the first one that we look at, because we're saying, okay, give us, we're actually I can't talk today. We're actually asking for 8 registers. The first one will be current. The second one will be output frequency. Third one will be the output voltage, etc, etc, etc. And we'll get those back as a list. We need to scale them up by these numbers here, which we'll be able to see in the code. So things like the voltage, we don't need to scale at all. The output frequency, we need to scale by a factor of 100. And the current, we need to scale by a factor of 10. But again, you'll see all this in the code. It'll make a lot more sense. But this is This is where we get this information from. And this is the trickier one to explain, but this is how we get that detailed information and that feedback of what in this instance is this VFD up to. Is it stopped? Is it running forward? Is it running, is it decelerating to go back to reverse? Is it decelerating to a stop? All of this really cool stuff we can work out from this bit pattern here. So that's the Modbus settings. So the first real thing we run into when we're running this main script is when we're trying to set this drive package, which is the user input side of stuff. So when we get here and we're looking to set these flags, what is actually happening? So we are creating a Modbus instrument, if you will. I've called it Turny Boy because we're trying to turn stuff. It's a VFD. So Turny Boy equals minimal modbus.instruments, blah, 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 blah. You've seen all of this stuff before. Again, go back to the previous videos to see how to set it up in depth, but there's no difference here. The only difference is instead of us actually typing in what these values are, where you can see here, MB, we're referencing everything in this Modbus setup script. So we can reference that from this script or a million scripts, it doesn't matter, because it's all the same stuff all in the same place. If I wanted to change one thing in here, it would change everything everywhere instantly. So that's very, very nice. But exactly the same as what we're all used to for minimal Modbus. So this is the function getUserDrive that is run in the main script. And all it does is print out a nice bit of stuff to let the user know what's going on, gives him or her a few prompts. So if you want to run it forward, type FWD, etc., etc. And then it sits and waits for the user to do just that. And it checks what has come through. So if it is FWD or rev or stop, this is where we input these numbers. So if we run forward, we want to set that second bit, if you will, not the 0th bit, the first bit, or bit number 2, however you're indexing them. So we return the integer 2. If we want to run in reverse, we return the integer 4, and if we want to stop it, we return the integer 1. If the user inputs something that is not one of these 3 specific things, we return the string drive error, and that, as you've seen, is handled here, and just lets the user know, please try again. And that's as simple as that is. That's all we need to do. The next thing that we run into is getting the user speed. Same as before, getting the user speed. We print out a bunch of stuff onto the screen to give the user some prompts as to what to do, and we just look at what's going in. Now, I said this is a bit more involved because there's a few things that can go wrong. So the user is going to try and input something, and we're going to make that equal to this variable called speed input. Now, as soon as they do that, it will take that in, and then it will do this try except thing. So first thing it's going to do is, a bit of a long story, but we're going to cast this to a float because this is so that you can input an integer or input a float. It doesn't really matter. So whatever it gets in, it will then make into a float. It will then times that by 100 because we saw that the hertz needs to be this magnitude of 100, bigger or smaller depending which way you're going, to allow you to do that, get those decimal places. And once we've multiplied that by 100, we then make all of this an integer. Because we were timesing by 100 just before that, we know we can definitely do that. We're not going to get rid of any information by truncating anything. So it tries that. If it can't do that, that means the user has input some text or something that basically can't be turned into a float and then turned into an integer. So that is bad. And if it does that, it will accept and just return not a number. And you've seen how we handle that in the main script. If that is the case, if that's not the case and the user has input an actual valid number, that has then been multiplied by 100 and made to this thing called speed integer, we move on to the next check. So here we're doing an actual kind of belt and braces thing, an is instance check, like is this variable here, speed int, is it actually an integer? So that's a nice little check you can do. If that is the case, we can move down here and we can do the final check of seeing if it's within the limits. So This VFD is quite nice. If we put in 20,000 or whatever and send that off to the VFD, it wouldn't accept that, even though it's out of its limits. The VFD itself wouldn't accept it, but it's always good to try and handle this in code and give out clean stuff to whatever you're doing, just be nice. And when you update equipment, just try not to put yourself in any nasty situations. So all we're doing here is checking if this integer, because now we know it definitely is a nice integer, is it between 0 and 6,000? If that is the case, which is what we want, we actually return that integer. So if we actually input 12.34, we would get returned to us the integer 1,234. Now, if that's not the case, we know that it's outside of those limits. So we return OL for outside of limits. And again, you've seen how the main code handles that being returned as OL. It just prompts the user to do it again. And for whatever other reason, if something weird happens, we return not a number, and that's handled in exactly the same way as this, and the user can just throw in everything again to try and get it to work. And the last little bit of this user inputs thing is if all of this has worked, this is the actual business end of the code, these 4 lines here that just send that data to the VFD. So you can see this is the function we call, and it's expecting these 3 arguments here. For minimal Modbus, when you're writing multiple registers, you are wanting to send where you're wanting to start writing from, and then a list of however many things you want to write. So if you send a list of 12 elements, it will write 12 registers, with each register being each part of that list. So what we need to do is make a list, which I've called send list. And that send list is made up of the first thing that we want to do, which is the speed. And the second thing is the drive, because in here, we know we need to put in the first thing here is the speed. And then the second thing we need to send is the drive mode. So that is why the list is in that order. So speed first, the 0th index of that list, and the 1 index of that list is drive mode. That gets turned into send list, and that send list is put into here. So we know where we're writing from, because we're pulling that data from, minusing the 40,001, etc., etc., and we're giving it the list as well. And we've created this instrument up here. So we just call TurneyBoy and tell it to write registers with this information. And once we've done that, we are good little boys, and we turn off our, we close off that serial port. Job done. And now that is all the information sent out to the VFD. It gets that information and does exactly what you've told it, with all the safeguards of knowing if a user puts in absolute gumph, it's not going to get fed out to the VFD, which is always nice. The last part of this code is, I can't see where I'm going, is here. So once we've done all of that, we've sent all of that information out to the VFD, we end up with this little part of code here where we're running this stat.read, which relates to this statistics display. And what we're doing here, exactly the same thing, but we're creating another Modbus, minimal Modbus instrument. I've called it Ready Boy because we're reading. Again, set up in exactly the same way. So again, we don't need to go into this. You can see it's referencing this same MB, this same Modbus settings script. So we don't need to change the settings in every part of our code. We just need to change it in one place, and those changes are reflected across all of these different instruments, which is really nice. All that happens here is, while this is true, because this is called, and then the code will just sit inside of this, because this is a loop in itself. The code will just sit in this loop and run and run and run until the user either wants to update what the VFD is doing or exit the program. So all we do here is this is the actual Modbus call here. So we make a variable called data, and we get that data from doing a ready boy read registers. The read start is where we're starting to read from, the MB read length is what all of the settings that we have before, and the 3 here is our function code. So it's again very well identical to previous videos. And once we've done that, again, good little boys and girls, we close off that serial port. And at this point, data will become a list of however many registers we've asked to read. And because we know the order of these, again, from the user manual, we know the first thing in that list will be the current, and we'll need to divide it through by 10 to get the actual current. The second thing will be the output frequency. We need to divide that through by 100 to get the actual value for that, so on and so forth. And this is all this is doing. It's just splitting out this data list using the indices. So the first 0th term in that list we know is the current, and the second index 1 is hertz, so on and so forth. And that easy. So the only real weirdness comes with this process variable here, which is looking at this 5th index, 6th index, if you will. So what this is, this corresponds to, like I've said before, this bitmap here. So this is actually saying what the VFD is doing. So if the very first bit, the lowest significant value bit is 1, we know it's stopped. If the second most one is, we know it's running in the forward direction, so on and so forth. It's not quite as easy as, this is 1, this is 2, this is 4, this is 8, so on and so forth. Because we have these reserved things up here, which are set to different values, but they remain constant, which is actually quite nice, because we can just run a bit of maths and work out what these numbers will be if it's in any of these particular states. So I've done the maths, and what these integer values work out to are these guys here. So if I know when we look at process here, if it is 24577, I know that the VFD is stopped, and I make our variable op equal to the string stopped. Same goes for accelerating forward, running in forward, blah, 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 blah. And each of these has these unique integer values that correspond to what it's actually doing. And if we run into a situation where it does throw out one of these integers that's not recognized, it just it makes op equal to the string unknown. So following that, all of this can go into a nice table for the user. So we call it a snazzy VFD viewer, because it is a snazzy VFD viewer, not so much for my video capture stuff anyway, but for the user it is. And here's where we do our divisions depending on what these multipliers are. So current 10, frequency 100, voltage 1, and output power 10. And you can see that reflected here. So our hertz is by 100, current by 10, voltage we leave alone for the output voltage and for the bus voltage, and for our power we do that by 10. And we've actually printed out the process number here, so we can see what number is actually coming out. And then down here we say the current operation is whatever that is in an English readable form. So it's decelerating in forward to go to reverse, or something like that. Now, again, all of this code is available on my GitHub, and that link will be in the description if you want to download it, play with it, do whatever. If you wanted to, you can uncomment this section here. If you uncomment this gives you extra information on what's going on, just to help you debug if you're having issues with well, whatever you might be having. It's just a bit more information for you to debug with. And then the last thing here, we just print out a prompt for the user just to let them know Control-C to go back to changing the settings or to exit the program. And this bit here is what is playing merry hell with my video capture. This works really nicely when it's just running, but when I run the screen capture, it goes all crazy. But this basically gives a delay, clears the screen, and then starts up again. So this just runs and runs and runs and runs and runs. until the user decides to do something. And when the user decides to do something, it will come out of this loop here, this loop here. And as soon as it does that, we reset the drive flag to false and the speed flag to false, clear the screen again, and the whole process starts over from the beginning. So let's have a look at this, knowing what we know now. Oh, it's still running. Kill that off. So we start the program again. And let's run this in forward. So FWD. In fact, no, let's mess that up. So we're putting a bunch of garbage when it wakes up. There we go. Bunch of garbage. We press enter and it says drive mode not recognized, which is good. And it brings us back to the same point to input a drive mode. So let's go forward. And let's try and put in something that's way out of limits. Way out. So speed under or over limit, which it is. Drive mode is still set to 2. So let's try that again and let's put in 60 going forward. And we can see here our hertz is building up. Output voltage is changing. Bus voltage shouldn't change too much. Obviously no current, no voltage because we're not plugged into anything, and we are running in forward. So if I change this to reverse, so I have control C and it's reset our flag. So we're back at the start. I'm going to put reverse at 60 hertz. And we can see our hertz is decreasing and our operation is telling us we are decelerating in forward to go to reverse. And that is corresponding to 28706. Now we've passed going backwards, now we're going forwards. Now we are accelerating in reverse. So this just gives you a up-to-date kind of overview of what is going on in that VFD. And now we're at full speed, we're running in reverse. And that is how you control a VFD with a Pi, just using a RS485 converter. It's really that simple. The nice thing about this is, if we go back to the code, 90% of all of this code, it's all to do with making it look pretty and making sure the user can't put anything crazy in there. The only real control bits are where is it? Yeah, so down here, so this is sending the commands to the VFD. So this is effectively writing, and then our reading, in the statistical display, when we read the VFD here. So they're the only two real actual, I don't want to say important, but that's the guts of it. Those couple of lines there, and the rest of it is setting up to do that. So yeah, with most things in coding, it's 5% making it work, 95% trying to make yourself look clever. So if you have any more suggestions or tips on anything you'd like to see me cover, please let me know in the description. So without further ado, thank you very much for watching, and I'll catch you in the next video.